So it tends to mean something different for everybody. If you're a network person, zero trust tends to mean your traffic
mTLS.
path, your plumbing, your segmentation. If you're an application person, it means something different again. Then storage, once again, different sort of domain. So it's a broad term, and if we really want to dig into the depths of it, what we can generally say across the board is zero trust is the prevention of lateral movement, inhibiting resources from accessing, engaging things beyond their immediate requirements. So what we're going to be talking about today is we're going to be looking at zero trust in the context of agents and together with confidential computing. So we're bringing it all together, and hopefully at the end of the session, you're going to know a little bit more about all those concepts lined up together. So if we're looking at securing data in IT ecosystems today, probably seen many similar slides to this one through the course of the day. We've got data in transit. So if we're looking at that from a network perspective, that's your MACsec, your IPsec, your quantum-aware cryptography, which supports your end-to-end. In the context of containerized architectures, that's your TLS with your service mesh, this sort of thing. When we start looking at data at rest, this is obviously your encryption of data, which is sitting in your Arctic storage or whatever storage medium you may have, to ensure that people can just pick up your data, walk away with it, and do something nasty. And then finally, and this is probably the reason why many of you are here today, is data at runtime, data in use. What is happening with our data when it's actually sitting in memory, sitting in the CPU, sitting in the GPU? Now, achieving zero trust is not one of these or the other. It's a culmination of many of these items together. And as mentioned, we're going to be looking at the end-to-end to understand how we bring all these pieces of the puzzle together to achieve a secure outcome. So coming back to zero trust, in the application space, we look at zero trust from a very broad perspective, which is your namespace security, securing your communication of one portion of your namespace to another portion of your namespace for your logical separation of your applications. When we start looking at micro-segmentation, in the context of applications, we start looking towards the concepts of things like service mesh, which provides you the ability to link up communications between different Kubernetes clusters and potentially having applications sitting in different clusters that have the ability to communicate with one another over a common orchestration ecosystem. Within this domain, you have security enforcement mechanisms like SPIF and SPIRE, which provide you the ability to secure your workloads. We're going to be talking more about this a little bit later. And then again, you've got the explicit permissions that are required to allow you to communicate from workload A to workload B based on a given trust. Then finally, this is where we start getting into the kernel level data, right? Nano segmentation in the context of application being your system calls, your database queries, your data objects which are accessible and visible at the kernel itself. We have some fantastic tools out there that allow you to access the kernel, which is great, but as a malicious actor, not so great. So that brings us across to the 4 A's. So you probably heard about authentication, authorization, and accounting. These are common attributes of anything to do with security of any system, be it network systems, be it application ecosystems. All of these components have been with us for many, many years, and they're all very, very important parts of how you build up your architectures. Attestation is probably 2026, the age of AI-driven security, vulnerabilities and threats. Attestation is that 4th A. We're looking beyond just the authentication, the authorization and accounting to the attestation. And this is just a small subset of the capabilities that we have within our toolbox to ensure that we're secure. Agents being one vertical. If we look at the AI ecosystem, we also have training and inferences, other key verticals that are associated with bringing everything together.
Yeah, so with that, we're going to take a step back from the zero trust piece and look at how agents actually run in Kubernetes. So if you go next, so you might be familiar with an agent application. It has kind of two requirements. The first one is you need inference, so you need to be able to reach out to some kind of model provider. Traditionally, people have been using ChatGPT, Anthropic, Bedrock, and then you need some kind of tool call. So you have to reach out to an MCP server or some database or a sub-agent, and delegate some tasks to some other either tool server or agent to do other tasks. So with that small system in mind, if we go next, we can look at how it actually runs in Kubernetes. So Josh and I have a cloud native background, so all of our examples are going to be in Kubernetes clusters. We're going to use K3s for our demo. So in Kubernetes, you might be able to run your user application, your agent, in Kubernetes as like a Kubernetes pod, and that might be running in a trusted execution environment. But your first pass of building this agent system might still have that dependency on the external provider. So you can still have egress policy for guardrails, injecting credentials at the egress gateway, so your agent doesn't have access to those credentials, but you still have this dependency on that external model provider. So can we add confidential computing for inference? The next slide. So one option you can take is using a managed provider. So there are managed providers that are appearing in this space, like I think Fala and Red Pill AI, that provide attestation for the model you're using. So you have some kind of attestation evidence that can confirm that you are actually reaching the model that you expect, and that model is running on attested hardware that you expect it to be running on. So that's a little bit better. But we're in the open source space, and we actually want to do everything ourselves. So if you go to the next slide. So Josh had some H100s lying around, and we decided to try this self-hosted approach. So in our Kubernetes cluster, if anyone's not familiar with how you do this from scratch, like taking confidential computing aside, instead of having that egress flow where you're leaving the cluster, instead now you have an ingress gateway. Think of Kserve or LMD is serving your inference, right? So under the hood, LMD is actually using the Kubernetes Gateway API inference extensions. So that's handling the routing to your inference pool, where you define all of your inference models. So the inference models are the things like your inference engine, so VLM, LGLang, all those. And instead of doing basic proxy routing, it's actually using an external processing endpoint picker that does more intelligent routing based on the KV cache locality or the LoRa loaded score. So with that, in Kubernetes, you can, if we take a step back and think about, okay, so we have this trusted execution environment. How do we protect our agents and our models? So very similar to traditional applications, you want to make sure the data that you have is only being securely decrypted and processed in your secure environment. So then that means you can isolate the compute, encrypt the memory, and have attestation of the hardware where your application is running. So in the AI case, if we go to the next slide, we have now agent prompts, so your user prompts are getting processed. That those prompts can contain secure PII data, like social security numbers, credit card numbers. Like in the previous example, booking a trip to Japan, that means you have to trust your agent with your credit card numbers. And then you might also have PII in the response. So the model might be trained on some kind of data that has sensitive data, and you want to mask that as well. And then your agent could have access to certain private keys you don't want to expose. And then there might also be proprietary model weights that you also don't want to expose outside of your system. So keeping these requirements in mind, we're going to have a motivating use case that kind of puts everything together. So the three requirements that you should keep in mind as we go through is data in use has to be protected, both at the CPU level and the GPU level. Our system has to prove that it's genuine, so the hardware we're running on is attested. And then finally, the data at rest also has to be secured, and that's separate from the memory, GPU, CPU security, and the in-transit security.
So thanks, Nina. We're going to jump into a use case now, and I was hoping it was a warmer day today because it would really resonate in summer. And I made the mistake of leaving
San
Europe,
Francisco.
which was much warmer than here, to come here for this use case. So we're going to walk through a fictitious scenario of an organization, an ice cream shop that makes the best vanilla, raspberry, and mango scoops of ice cream on this side of Main Street, called Scoop Dreams. Now, Scoop Dreams decided 2026 is a good year to put everything possible in the direction of artificial intelligence. So they started out thinking, okay, let's save some money and go with a rented rack for our automation and our agentic capabilities for our ordering system and customer loyalty system. So we can see the AI agent Scoops was basically set up to take in key customer data, social security numbers, allergy information, so that when the customers decided to bulk order, they'd be getting the right recipes, the right shipments without having any challenges. So everything was going well. We had the system doing classification. Everything was looped in with different agentic processes in place where the identification of all information was noted down. But the challenge was it wasn't secure. The runtime environment wasn't safe, and eventually a malicious actor got in and basically exposed all of this information, the social security numbers, the allergy information, knowing that, you know, peanut allergies, everything else, all this data which is supposed to be secure ended up getting into the hands of Rocky Road, which is the competing ice cream chain over the street. So Rocky Road somehow managed to get all of this information through scraping the runtime memory of Scoop's agentic system on its rented servers. And even worse, it got the recipe for the raspberry vanilla mango special, which everyone loved so much and was queuing up outside the ice cream shop for. So this was a catastrophe. The data was leaked, customer loyalty issues, you know, reputation risk, really not a great situation. So how do we get around this? What do we have to do? So I think everyone here at this conference has some idea, right? And that is, let's get a private, secure, robust setup that doesn't leak information. So once again, similar flow to before, but this time, instead of having critical customer information available in the runtime in the memory of the AI agent, it's secured in a protected, secure manner using private, trusted execution environments for the management of the data. So this time, not only is the data which is being classified and generated from the different customers being managed in a secure way, nobody can actually get in there. Rocky Road can't come across and try and steal the next summer's recipe. And attestation is giving us the full view that everything is secure perpetually. So not only do we understand what's at risk and what the state is, but we understand that it really is secure, not just thinking that it's secure. So Rocky Road is no longer going to steal our business. Everything's working the way it should be through the use of confidential computing and security and attestation of the runtime environment. Now, if we have a look at what's under the hood here, because that's a nice story, but without actually seeing some real data, it's just a story, right? So what we actually built, and we built this architecture in the system which Nina was describing before, we have a reflex pattern for an agent, which is basically leveraging two separate GPUs for a two-stage extraction pipeline, whereby Scoops the agent is taking in the synthetic records, which consist of social security numbers, API keys, and cardinality of data together to basically perform one stage, which is a prediction of the data which should be grouped together. Then a second phase where those sensitive fields go through a classification engine using a secondary on-prem model to basically decide, is it restricted? Does the data have to be encrypted at rest? Is it public data? How should we deal with all the different data? So this pipeline is active, and we deployed it for real using two different agentic frameworks. Does anyone know what DSPy is? Show of hands. Okay, so DSPy is a research framework which is quite often used in certain universities and research institutions. There's a variation thereof, which is an alpha release called DSRS, which is an agentic framework based on Rust. Why Rust? You have superior runtime memory hygiene in Rust, and if you look at the numbers, it's much more expedient to perform the actions you actually want to perform. So we tested the architecture in terms of penetration and exfiltration, not only in Python, but also in Rust, and we're going to see some of those results. So looking at the underlying system, what do we actually have up and running here? So we've got a Kubernetes cluster, which is running Kata containers. We're running confidential computing here. We've got the GPU device plugin, which is doing pass-through into the Agentic ecosystem. And we've got security foundation set up with hardware attestation, service mesh that we were talking about before for your data in transit encryption. And at a runtime level, we're using Cilium as the CNI, and we're basically using Tetragon to verify whether the memory is being scraped by any malicious actors. So there's a number of components we brought in together to achieve this, whereby we've got the agent layer, which is basically sending inference requests across to a gateway, which is using LLMD for model-aware routing. And then that routing per model is taking place across to our GPU farm to ensure that the right VLLM model is being invoked, be it GTP OSS 20B or Granite. So this is essentially our setup here, and we're going to actually see it in action very, very shortly. Now, looking at what we tried to do to actually penetrate the environment. This Sankey diagram here shows for each different runtime environment the penetration techniques that we attempted to use. So for our memory, we have a certain set of techniques, CPU, a handful of techniques, and GPU also. So this is our overview of essentially the different methods we were using under the hood, and a short list of what was blocked and what wasn't blocked before and after, so we can really see how the environment was behaving based on these different exploit levers. Now, if we have a look at the examples of exploitability, back to Nina. Sorry.
I can do this part. So our first example is going to be the data in memory exploit. So in this example, again, same Kubernetes cluster as Josh just walked through, but we have a host that's been compromised. So Rocky Road has access to our host. So we can use the exfiltration examples in the previous slide to access the process RAM that's shared with the host. So we have our agent application running in a pod in Kubernetes, so that it's a K3s cluster, but the PII information that the agent uses is accessible by the Rocky Road that's compromised our system. So let's see it in action. So on the left, we have the RAM without confidential computing. On the right, we have RAM with the Intel TDX. Sorry.
So here we can see the differences between the two environments. With the red one being where we're breaching the memory using our techniques shown before, and on the other side here in the green, we can see that the memory is secure. So we weren't able to actually exploit this the memory.
Yeah, and going back to our diagram, so in the secured case, so on the right, what we did here was just put the entire Kubernetes cluster in the TDX conventional VM. So the host, even though it is compromised, can't access the private TD RAM. So now a slightly different example. So we're going back. We're no longer in that secure VM. So we have our insecure Kubernetes cluster again, but this time we're going to do a slightly different exploit. We're going to use Hubble to see the inner pod traffic. So as our agent application calls out to the VLM endpoint, so that's the HTTP post V1 chat completions request, we're going to intercept that traffic. It's plain text traffic, so we can see the PII from there. So on the left, that's the exploit.
So as we can see, we've got Hubble, which is interacting between the different pods within Kubernetes to basically take the packets and reveal the in-transit data. And here we can see we've got a breach there in the red. And again, with confidential computing and, of course, mTLS, we're mitigating that attack.
Yep. So before we were able to see in the example the social security number and the credit card number in plain text. Now we're going to do two things. The first thing is we're going to run our agent and our VLM in confidential containers. So that's the Cocoa piece there. And then we're going to encrypt traffic between them with mTLS using Istio. So Istio is a service mesh that runs in Kubernetes. There's kind of two modes you can run it in, like ambient mode with a node level proxy or sidecar mode. So that means the traffic between the two pods is encrypted with mTLS. So our compromised root can't do the Hubble inspect exploit and see the plain text traffic anymore. So our final example is the data in GPU. So in this example, we have the same environment as before. So our agent application and VLM are running in those confidential compute environments, but we haven't secured the GPU. So that means the host has access to a bunch of shared components like the NVIDIA driver, the NVIDIA device plugin, and a bunch of GPU extraction tools from the previous slides. So that means that the Rocky Road is able to inspect the H100 VRAM and see the secrets from there. So if we see that in action in the next slide. So on the left, we have the GPU VRAM without the conventional computing, and then on the right, we have it enabled.
So again, we can see that the scenario where we have confidential computing up and running and we actually have the right security levers in place, we're actually preserving and securing the environment without, it's extremely fast to hack and remove that information, right? It's not taking much. This is a real example of how rapidly you're able to basically extract that information.
Yeah, so in the secure example, again, the only thing we changed is the GPU is running in confidential compute mode, so the host doesn't have access to the drivers or any other things that it could use for the exfiltration.
Okay, so bringing it all together. So we saw a number of different scenarios from data in transit and CPU and memory and GPU, where using the right confidential computing techniques brought us further forward to avoid various breaches. That's not where it ends. If we look at going beyond the compute, the GPU, the CPU, and the memory, we've got scenarios where we've got cluster to cluster. And when we start looking at agentic patterns where you have AI systems with agents really going all the way over the internet, then other things come into the visor, and that is, how do we actually attest and secure our routed path through the internet or our routed path through a private network? And also, what methods do we have to actually secure and attest the workloads themselves? So there's methods such as SPIF and Spire, where there is an ability to do attestation of the workloads. And within the routed platforms, just like your hardware platforms, your compute, you can perform attestation to verify that it's actually working in the way that you actually want. Now, this is a very noisy slide, a lot of information, but we're bringing sort of mini building blocks together from your compute in a fog at a distant edge, which could be at a desert, a field, an oil pipeline, to content delivery networks where you're potentially doing AI prefill at an early stage before going up to your public or private clouds, whereby you're performing heavy lifting with your AI models. All of these domains can be attested, secured with your data in transit, your data at rest, and your data in runtime. In addition, looking at your routed paths, you can attest the forwarding path through the internet, through your networks, to ensure that only routers, only network devices that have had attestation take place to verify that they're trusted become a path along the way from A to B. So building all these layers on top of one another, you can build a very, very secure and robust architecture. But it's many steps that need to be followed one after the other. But effectively, this view, this blueprint, gives a glimpse of how you can chain certain activities together to secure your software supply chain and secure your end-to-end agent and AI architectures.
Yeah, and to recap, we didn't cover some things that you might be wondering where are they, because agent security doesn't really stop here. Like there are things like agent identity that previous talks have covered that are equally important for zero trust. Tool authorization, guardrails. So there's a lot of guardrail providers out there. Governance, explainability, and benchmarking are also all very important for building secure agent frameworks. But at least today, our talk kind of focused on removing the weakest link across both like GPU, CPU, memory, transit, and at rest. Yeah, hopefully you learned something about running agents in Kubernetes securely. Thank you.
So, thanks a lot, everyone.